Can I introduce our first speaker for the afternoon session? Michael Lambert, who is speaking on joint work with Evan Patterson on representing knowledge and querying data using double-functorial semantics.
Thank you. Well, thanks everyone for coming. Thanks also to the organizers for putting on our conference. Yeah, this is a report on some joint work with my co-author, Evan Patterson. We did most of this work a couple of years ago in the summer of 2022. We got around finally to writing up the draft preprint, and that's on the archive. Take a look at it. Right, so yeah, we're going to be talking about representing knowledge and querying data. I believe the innovation here is the use of double categories. So I'm going to try to illustrate that throughout. This is at once kind of a very high level sort of overview or advertisement work that's in the paper. We're also going to look at some examples. So let's just start off with a question. What is knowledge representation? Maybe it's a little bit of a vague question or sort of a vague phrase, which I will answer with, I don't know, maybe sort of an esoteric one. Ontology logs, or O-logs for short. What are those? Schematic representations, basically. Let's just say concepts, attributes, and facts about them. What do these look like? Well, so concepts are very flexible, right? Think of a concept, arginine, for example. We schematically represent these in boxes. Attributes are arrows between concepts, and facts are equational statements that say that different paths given by attributes between concepts are the same. If that kind of looks like a diagram in a category, well, that's kind of the conceit behind O-logs. Generally, we think of or identify objects and concepts, identify attributes and arrows, identify facts, community diagrams. So an O-log is kind of like a small category in some sense. And in practice, we take these to be quite unprecedented, and we're thinking of an O-log sort of generating a small category. These are often identified with certain types of database schemes. These are small categories, right? So there's kind of two vocabularies here, one of knowledge representation and one of databases. We're going to kind of go back and forth between those. And so in this vein, in as much as an O-log is kind of an abstract framework for relationships between concepts and attributes and things like that, and it's merely abstract, we can instance the abstract knowledge base or scheme with a set valued functor, which we can think of as populating the abstraction of actual things or actual entities. We typically represent these as tables. So here's an example. This is one of these more or less sort of standard employee department examples. The main type here is one for employee. Every employee is in some department, every employee has a first and last name, and every employee has a manager. There are no facts here. This is relatively simple. And we might instance this with a table where every attribute is a column in the table. We notice here, right, that these attributes are all functional in the sense that every employee has one first name, one first last name, one manager, works in one department, etc. These examples are all very sort of standard. I've actually listed these straight out of the references on this material. These are what I think of as being functional O-logs, right? These are indexed by categories, and the attributes are supposed to be functions. But not every relationship between concepts that we might like to formalize is merely functional. So my co-author Evan Patterson came up with this idea of what I like to think of as relational OLOGs. There's a lot more machinery involved in this definition. If you know about such things, he basically said, well, a relational OLOG is a small bicategory of relations in the sense of Carbonian-Walters. And in particular, such a thing as a Cartesian bicategory. These definitions are kind of a mouthful. They're fairly abstract, but generally the idea is that the arrows are supposed to include relations, genuine relations, not just functions. And these are way more expressive, right? The relations friend of, enemy of. Hopefully everybody has more than one friend. Hopefully most people have no enemies, right? These are not necessarily functions. We get the functions back using the definition that Carbonian and Walters give of maps, which are supposed to be functions. So it's kind of a generalization of the purely functional perspective. The issue is that, like I said, Cartesian bicategories are pretty abstract, they're a little hard to work with. There's a lot of overhead in kind of getting into the definitions. The thing that I find kind of frustrating about the purely bicategorical approach too is that since the relations are encoded in maps, there's a bunch of equations associated with this. So from an implementation perspective, if you were to try to base data structures upon such a thing, actually code it all, you're going to have to ask for a bunch of equations, and that's computationally not terribly efficient. So that makes equational reasoning hard. Maybe there's a different way of doing this that actually gives you the expressiveness of the relational viewpoint that makes the functional reasoning easier. And that's where the double categories come in. So we've already heard double categories mentioned. I'm presuming this to be like a ground level exposition. So I just want to remind us what a double category is. This is how I think about them. We've got ordinary objects, arrows, just a category. You also have a second class of what are thought of as arrows, namely pro-arrows. These go, once again, between objects. I display them horizontally like this. They have a slash on them to distinguish them from the ordinary arrows, which I display vertically like this. Relating all the structure are these cells, right, which have an internal domain, internal codomain, and an external source and target in the form of ordinary arrows. There's an external composition for pro-arrows and cells that's associative only up to isomorphism. Arrows do compose strictly associatively. Lest these be a little bit esoteric seeming, there are, as I'm sure most of us know, tons of examples of such things. Sets and functions and spans form double categories. Sets and functions and relations form a double category. Categories, functors, and profunctors are a double category. Ring modules, metric spaces, and cosets, for example. Genuinely, this perspective is a generalization of both bicategories and two categories in sort of orthogonal directions, in that the pro arrows, a bicategory is a double category where all the ordinary arrows are merely trivial. The two category is a double category where all the pro arrows are trivial. And likewise, any double category has an underlying bicategory, which is given by the pro arrows, and an underlying two category, which is given by the ordinary arrows. I like to think of these as the relation, as like the relational part and the functional part. And so that is kind of what's going on here, that we're looking for some kind of double category with some extra structure that gives us something like a double categorical OLOG that would generalize both the relational OLOG and the functional OLOGs. So that's what we're going to work up to. We need some more structure though, right? The relational OLOGs were in particular Cartesian bicategories, and that structure is used. So we want something like a Cartesian double category. Well, what is that? Well, there's a definition of such things. We want the diagonal and the unique double functors to each have certain right adjoints in a nice 2 category. It's also convenient to ask that these double categories are equipments, which just means that the source target projection from the category of pro arrows themselves down to the pair here of ordinary object and limited arrows is a vibration, or equivalently a bifibration. And so we're going to cook up to a nice generalization here, and the theorem that I think kind of makes this possible is that if you have a locally subtle Cartesian equipment, right, having this and this, then the Y category underlying it is a locally subtle Cartesian equipment. And so on the basis of this result, we make a definition that a double category relations is a locally subtle Cartesian equipment satisfying in its underlying Y category the extra axiom that Carboni and Walters asked for that distinguishes bicategorical relations from the Cartesian bicategory. And we'll define a double categorical O-log to be a small instance of such a thing. So the equipment structure and the Cartesian structure will actually do some work for us shortly. So let's say what this means a little bit more precisely. Basically, this is equivalent to saying that every niche and every co-niche fills in and has either a restriction or an extension respectively. The restriction here fills in the niche with a Cartesian cell, Cartesian relative to the source and target projection, whereas on the other hand, the co-niche is filled in with an extension cell here, which is off Cartesian with respect to the source target projection, meaning that these 2 cells each have nice lifting properties. This is abstract. So in relations, for example, you can actually compute these by hand, right? Extensions, well, sorry, restrictions, roughly speaking, pullbacks, extensions, roughly speaking, are images. Now, these constructions will let us do some manipulation of data and also to help us to form more complex ideas and propositions in our O-logs. So let's also talk about the Cartesian structure briefly. This is basically saying that the categories of ordinary arrows and then of cells each have finite products. And these are related to each other nicely with all the external structure functors. And as a result, every Hahn category of pro arrows with fixed objects, right, has local products in the sense that it has, well, each one has all finite products. And for example, you can construct a terminal as a restriction, and you can construct the local product of 2 pro arrows, let's say M and N, by a restriction along the diagonals, which are given to you by the fact that category D0 has those products. Great. So now that we know a bit about abstractly, right, the sort of framework, I want to try to illustrate the use of the framework in some examples. I don't really like the employee-employer examples necessarily, so I've drawn to one of my favorite shows on television, Stargate SG-1. If you haven't seen Stargate, that's fine. You don't need to have seen it. Roughly speaking, wormhole exploration of not just this galaxy, but other galaxies, ancient aliens and stuff. It's pretty fun. So if you haven't seen it, it's highly recommended. Highly recommended. First of all, I want to make a point. First point is that these structures are genuinely more expressive than just the functional or just the relational perspective. So I'm going to posit a concept of system lord and a concept of Jaffa. System lords are basically rulers of the ancient aliens, and the Jaffa are their warrior slaves whom they need to actually enforce their rule across this galaxy anyway. And I'm going to posit some individuals here. One is a system lord and one is a Jaffa. These I intend to be sort of functional errors, right? These are constants in the logic that are picking out individuals. Now, let's say we want to assert a fact. So every system lord has a first prime, which is sort of like the leading warrior among all of his Jaffa armies. And so there is an attribute here, system lord Jaffa first prime, right? Thinking of every system lord having one first prime. And so I'm going to assert the fact that Tilk is first prime of Apophis. That is just to require this diagram to be commutative. Right. So this is kind of the functional way of doing things, right? And this makes perfect sense. But maybe the relationship between system lord and Jaffa of first prime is not necessarily, or we don't want to think of it as being functional. Why would we maybe not want to do that? Well, there are certain system lords who've been deposed, and maybe they've lost all their Jaffa armies, and so they wouldn't have first prime at that point. Maybe Jaffa had served more than one system lord as first prime. Maybe the system lord still has all his armies, but he's between first primes or something like that. Maybe he's had multiple first primes. Well, let's stipulate that instead we're interested in the relation first prime. But we still have these individuals that we want to talk about. Well, the individuals are the functions and the relations the relations. So now we can actually look at a genuinely double categorical statement here, something like Tilk is the first prime of Apophis. We can actually form the proposition here with a restriction cell. Is it true? Well, not necessarily, but we can, in the old log, stipulate as truth by just requiring that pro arrow is in fact equal to the terminal in the hum category. But we could also, for example, analyze, right, the extent to which this is true if we didn't want to stipulate or require as truth. Great. So in other words, right, genuinely we can build things that are very expressive and rather straightforward. So what about manipulating data? I believe the innovation here is in some kind of loose sense like model theory. So structure preserving functor from some category C with structure to D is sort of a model of C in D. And so let's just define, right, a data instance for a double O log to be a Cartesian double functor valuing relations. If you want to think of everything here being sort of strict, that's fine with me. In implementation, everything is usually. We don't need to ask that the equipment structure is preserved because double functors automatically do that. And so the last, or not the last, but the second point that I want to make is that data manipulation, in particular querying in relational databases, comes down to functorial semantics. How this is done right now, as far as I understand it, although I'm not necessarily up to date with the state of the art, is in the functional viewpoint. If you wanted to do a query or manipulate or sort of migrate your data somehow, what you would have to do is set up another scheme, introduce some kind of translation functor that would actually perform the operation, and then you can use these external adjoints in the co-creative categories to perform the manipulation that you're looking for. And so the substitution functors like a select and the right and left adjoints are various joined tables. From an implementation perspective, as far as I understand it, this setup is again computationally expensive. So the thing with double categories is that all of these operations of querying and manipulating can be done just by working in the double category and then just trusting that the instancing functor does what it's supposed to do. So in particular, right, select, filter, and join are basically just computing restrictions and extensions in rel, which, as we've seen, are pullbacks of images. So let's look at another example here. I like this example in that it sort of illustrates a little bit of my philosophy of double categories here. I like to think of the pro arrows actually as being second class of object rather than second class of arrows. And so this might elevate mission to some kind of, well, it's a concept, right? But also it's kind of an entity, right? And it's being tagged with dependency on other concepts. A mission should occur on some date. It should occur somewhere. It should be to some end, and someone can carry it out, right? So we can instance this with a table, for example. And here are my rows. These are all, I think those are the air dates of the episodes. These are some planets where the missions actually take place. Cimmeria, for example, is a nice spot where SG-1 assisted the Cimmerians in their uprising against the System Lord, who actually controlled that particular planet. There's a search and rescue operation here on Net2, also carried out by SG-1, etc. Right? So let's say we've got this data table, right, in our database, and let's say the purpose and location of the mission is irrelevant to us for whatever reason, and we just want to know when more our team's offboard. Well, we can do that. We can just project, right, ignoring the location and the purpose, and then we extend, and then we get a new proposition here, just data team. And in order to figure out exactly what the data looks like, we'll just use the instance, and we'll compute the image in relations, which is a new table, just date and team. And this is precisely a select operation in SQL, for example. Great. Say, on the other hand, we only care about SG-1 missions, right? They are, for example, the titular team of the show. So we could stipulate an individual constant, right, SG-1 of team type, and we form a restriction cell. And this gives us, well, essentially a new proposition here. We're just looking for SG-1 missions. And again, the instancing data is going to preserve the restriction and the Cartesian structure. And so this returns a new table, SG-1 missions, right, where we now just have the rows corresponding to the missions SG-1 carried out. And this is filtered in SG-1 in SQL. Great. One last example of computation. This one's a little harder. This is the join of two tables that have a column in common. Abstractly, this is kind of what it would look like. Imagine that P and Q are tables, and they share a column B in common. If we were to join these, we would form a restriction here along the diagonal from B. I want to apply this. So here's another O-log. Again, I think instancing the flexibility, right, of this framework. We have one pro arrow for expertise and one pro arrow for membership. Every person, hopefully every person has a skill, right? Might have multiple skills, but not every person is on a team, although each person who is on a team should probably just be on one team, right? So I'm going to instance these with some tables here. Hammond, his skill is command. We've got law, combat, command, archaeology, sociopathy, I guess is a skill. Yeah, I'm editorializing a little bit. Now, all of these persons, right, and the membership table are also persons in the expertise table. However, not every person on the expertise table is on a team, right? Only these 5 individuals are actually on teams. So perhaps, right, we have these 2 tables, and we want to look at the person and expertise in which team they're on. Well, that would be a join, right? Each of these has a person instance in common, and so we're going to form this restriction cell where we pull back along the diagonal for the person type, and then we'll just compute the corresponding pullback in relations to see what the table looks like. And this is the join, right, of the expertise in the membership tables, where we're just getting the individual with his skill and which team. Great. Yeah, and this right is the join in SQL. Okay, fantastic. So we have shown right that we have lots of ability to do standard operations in like relational databases in SQL, for example. I like to call this data munging, which I think is a phrase that's used in the field, which I think is kind of funny. So where are we with the implementation on this stuff? Evan and I spent the summer, like I said, in 2022 working on the material. We programmed a bunch of generalized algebraic theories, a bunch of GATs in the cat lab, implementing data structures based on, well, we did Cartesian double categories and equipments mostly. We revamped the double category stuff. There was a bunch of stuff there already on categories, on ordinary categories, monodal categories, and bicategories. This is all done in the Julia language, which is like a high functioning, very fast language for data science. A lot of questions, outer joins. There are people who think that's not a super important problem, but I don't know, maybe. We'd like to program relation value double functors. I'm very interested in whether there's some kind of query language here in the background. I honestly have no idea. We'd like to do full data migration at some point, which would involve being able to actually set up translation functors between OLOGs. And then the migration would actually be operations using adjoints between virtual double categories, lax double functors, which is a lot of work. So that's kind of on the horizon. Like I said, this is basically an advertisement for a paper draft, which should appear in the proceedings. For now, it's on the archive under this address. I also wrote a blog post on this about 18 months ago that's still up. And you can take a look at that. That's all I have to say, so thanks a lot.
Time for quick questions. Rick first.
So I saw a lot of double categories. Really use all of that. And a related question. What do you think of this?
Well, for example, we use Cartesian structure right here. Yeah. And which spin-off series? Is it Atlantis or the other one that we don't talk about? Atlantis is banger, is great, but Stargate Universe,
Talk a lot of coffee.
You can ask either of these two. This is like prompts, like an LLM prompt, LLM prompt. So one is aggregation, another is like nested types. Like
sure. I'll talk about it after. Sounds like what I don't know about.
So relations have a domain and codomain.
Yeah.
But it seemed like the semantics you were using didn't really distinguish between those.
Yeah.
So could you maybe speak to that? Why should you arrange things in this relation thing, and do you need ever to put things on the other side?
At this point, there is not a huge need to do that. If we use double category relations, there ends up being some compact code structure that essentially doesn't matter where it comes. But I think there are relations where it kind of does, in that semantically, right? A relation like parent of, I think that kind of matters. Right? Like you sort of like want the individuals who are the parents and the individuals who are children sort of on opposite sides in some sense, right? Otherwise, it seems like it might not matter in some grand sense, but if you want to convey an idea, right, of parenthood as sort of relating like this way, yeah, maybe it matters. In which case, there's a lot more theory there, and I don't exactly know what it looks like.
One last question.
me?
Yeah.
Yeah.
If you instead of rel, you take
the double category whose horizontal morphisms are quasi-morphisms for like the functor that sends a set to the set of finite subsets of that. Is that still an equipment?
Offhand, I have no idea.
Okay, because I feel like, in database theory, like a table is always finite,
Yeah,
right? But if you
Yeah.
only do relations that are finite.
that's a good
yeah.
point. Yeah, good question. I suppose this framework allows, not necessarily finite stuff, which I don't know, maybe I don't know. Maybe you heard about that, maybe you don't, I don't know. I don't know.
Well, I suggest that we keep the rest of the questions for the coffee break, where my list of.